As Megan O'Sullivan shared with us, one of the major imperatives of the next few decades is the transition from fossil fuels to net zero. And thankfully, we have an expert to discuss that topic with us over the next hour or so. Dr. Lawrence Makovich is an energy economist focusing on research into the electricity sector and climate change issues. He began his career at National Economic Research Associates, and over the past 40 years, he has held senior research positions at DRI McGraw-Hill, Cambridge Energy Research Associates, and IHS Markit, as well as having taught at the Northeastern University Graduate Business School. He was appointed to a senior fellowship at the Mosavar Rahmani Center for Business and Government in the John F. Kennedy School of Government at Harvard University, where he published Tilting at Windmills, Making a Case for Reframing Electric Sector Climate Policies. He's published numerous other articles and reports, as well as testified before the U.S. Congress, state agencies, and the Federal Energy Regulatory Commission, along with having made presentations at conferences, board of directors meetings, and the Harvard Electricity Policy Group meetings. He holds a BA from Boston College, a Master's of Arts from the University of Chicago, and a PhD from UMass Boston. Welcome, Doctor.
Thank you, Dan. Well, thank you, Dan, for the introduction. And Andy, thank you for the invitation to participate today. And thank you, Megan, for setting up the topic. It's an important topic to confront the costs and benefits of addressing this big issue of climate change. And one of the reasons why I think it's so important is that there are many influential politicians as well as academics that think we can address climate change without really confronting cost and benefit trade-offs. So I'll start off with an example here. So this is the current Secretary General of the United Nations, Antonio Guterres, and he's telling us that we've got to limit global warming to 1.5 degrees above the Celsius, above the pre-industrial level. That means we have to get to this net zero anthropogenic emissions. And as Megan says, what they mean by that is what human beings are going to put into the atmosphere, human beings have to use technologies like that carbon capture, utilization, and sequestration to pull an equal amount out. We need to do that by about 2050. And then we've been also told that the world can shift away from fossil fuels because cheaper renewable alternatives are available. So here's a nice win-win situation here. Now, Megan also gave us a little bit of the background here. So the UN set up the IPCC, Intergovernmental Panel on Climate Change, in '88. Its mission is to give people and governments the information they need to put together their climate policies. And so to do that, what they do is periodic multi-year research that culminates in these climate assessment reports. So AR5 was the last one that came out, and they're in the midst of putting out the AR6 assessment. And they roll them out in draft form and in parts, a summary report, and then a final report. And so we've just seen, although the AR6 final report we've only seen in draft form, in March of this year, we saw the final version of the summary report of AR6. So that's a new piece of information from the UN to try to influence policy formation. And this idea is actually quite appealing, that we can address climate change at little or no cost by just switching over to cheaper renewables. And as appealing as it is, it has the unappealing effect of stifling conversations about costs and benefits. And I saw this firsthand when I attended the COP meeting, that conference of party meetings that the UN puts on about every year now. I went to the one in Katowice, Poland, and I was in an auditorium like this with a couple hundred people waiting for an hour-long presentation by the US delegation to give us an update on where's climate policy going in the US. And so they introduced the US delegation. They were about to speak, and the front row had a couple of dozen climate activists who got up, pointed at the podium, and started to laugh and cackle. And there was a small group of security folks on hand that let them have their time and then physically helped escort them out of the room so the presentation could restart. As the delegation got ready to restart, there were another couple of dozen sprinkled throughout the audience that stood up and started to chant, "Leave it in the ground, just leave it in the ground." By the time additional security got there and helped all those people out of the room, there was no time left for any presentation or discussion. So, you ask yourself the question, well, where does this idea come from that the world can or should simply leave fossil fuels in the ground? And so, here's an example of a very prominent academic. So Jacobson's at Stanford University, and his partner there was at Berkeley. And they put out some very influential analysis. It was published in Scientific American and then the Proceedings of the National Academy of Sciences. And what they say is, look, with the available technology, and this was technology available about a decade ago, the world can transition by electrifying everything and then powering it 100% with wind, solar, and water. And we can stabilize energy prices, lower energy bills, save lives, and create jobs. A nice win-win appealing idea. Now, they did that to influence the upcoming COP21 meeting in Paris, where people were trying to formulate climate policy. A couple years later, after the COP meeting, there were 21 energy analysts, including some of his colleagues at Stanford, who looked at this. They evaluated the study, and they said that the work seems to have used invalid modeling tools, contained modeling errors, made implausible and inadequately supported assumptions. Other than that, it looks like they liked it. But policymakers should treat with caution any visions of a rapid, reliable, low-cost transition to systems that rely exclusively on renewables. So, despite this, and I have not yet seen any real good analysis that suggests that there are options out there right now that's going to enable a low-cost energy transition in any kind of rapid time frame like 2050. However, this January, the White House just released its guidebook on that Inflation Reduction Act investment in clean energy and climate action that Megan had referred to. And if you read what the guidebook says, by implementing the policy options, many of which were kind of shaped by this idea, let's electrify everything and move more towards renewables, that by doing this, we're going to lower costs for all Americans, create good-paying jobs, address the cumulative impact of pollution on disadvantaged communities, and ensure that America leads the global clean energy economy by reducing its greenhouse gas emissions 25% across the next 7 years. So another idea of a win-win solution that's very appealing and has real staying power because I think people want to believe it. So I thought, well, if I'm going to present some analysis today, I think I'll try to say something that's going to be appealing that everybody can agree with. And so I'll start off by saying the best things in life are free. So I think we can all agree on that. All right. The problem, though, and here's the rub, that some of the things that aren't free are things like shelter, food, clothing, and medical care. All right? And so one of the defining characteristics of our human condition is that we have to work in order to produce the goods and services that we need. Now, what does this have to do with energy? If you Google what is energy, you'll be able to pull up the U.S. Energy Information Administration website, where they'll tell you scientists define energy as the ability to do work. Right? So to get the work of getting the goods and services we need, we've got to use energy. So to see that, we need to use models. And so the National Academy of Science gives us some good criteria to judge the use of models in analyzing the way we harness energy and have to address climate change. And there's a couple of important things they say here. And the big one here that we'll focus on today is, if somebody gives you an assessment and they make a prediction, and the world turns out very different, it's likely they missed something. And we're going to see this as we evaluate what we're being told about climate. So, if we look at the way we harness energy in the world today, this simplified model of the current global production process helps to give us a sense of what's going on here. Now, if you look at the EIA website there, besides the definition for energy, they'll tell you energy comes in 9 basic forms. One of the defining characteristics of energy is it predictably converts from one form to another. And so we can add up all the energy inputs, the coal, the oil, the natural gas. We can even add up the energy arriving from the sun that we harness with photovoltaic panels, and we can all express it in one form of energy, thermal energy, heat, BTUs. All right? And so we've got about 601 quadrillion BTUs that people use every year, along with other inputs, with the available set of technology to produce the goods and services that we all need and want. Now, given the state of technology, we also have the problem that we have some byproducts here, that we have accidents, injuries, deaths, and as a byproduct of utilizing fossil fuels, we get the energy from fossil fuels by using a combustion reaction that takes the chemical energy in these fossil fuels and converts it into the heat that we harness to do all the work we need to do. But a byproduct of that is that we produce CO2. So right now, on an annual basis, the world is producing about 34 billion tons. A gigaton is a billion tons of CO2 every year. All right, now, one of the things we realize is when we look at those goods and services that we produce, we don't produce enough to satiate everybody's needs and wants. So as a result, we've got scarce outputs. We need prices to allocate that to people on the basis of the distribution of income. Now, what's interesting is this also explains, in part, the distribution of income, because this ongoing production process, how are people able to afford to buy all the goods and services? It's because those revenues flow back and get split up as payments to labor, human capital and wages and salaries, as returns to people that own the physical capital, rent for land, and payments to people that own the raw materials that we need in this input process. So, because of that circular flow, the dollar value of goods and services at their prevailing prices is also a measure of aggregate income, because it all flows back in one form or another as income to the factors of production. So, global aggregate income around the world was about a little over $12,000 per person in 2021. Now, to put that into perspective, in the US, we're close to 6 times that level. All right, so when we look at different countries and look at income per capita, it reflects energy harnessed per capita. So you can see that relationship that exists there. So to get the work done to produce the things we need and want, energy is a very key input here. Now, income per capita is not a direct measure of economic well-being or the standard of living, but it's highly correlated. So the World Bank sets a criteria for poverty. They've also made an assessment of current living standards, and they conclude that half the world's population lacks access to modern energy services. More specifically, the International Energy Agency tells us that in 2001, 768 million people on Earth, that's about 1 out of every 10 folks, don't have access to electricity. So you can get a sense for the kind of benefits that people are looking to harness by harnessing energy and growing output per capita. Now, the other thing that we see here, if we look at this data, country by country or even within a country, is that lower income consumers spend a higher percentage of their disposable income on energy compared to higher income consumers. So in India and China, aggregate income, energy purchases account for about 10 or 12%. In the US, we're about half of that, of aggregate income per person. So the implication here is that if we do climate policy that increase the cost of energy more than we have to, that cost burden is going to fall disproportionately on people with lower income. It's going to have a regressive cost impact, which is why it's so important that we look at these costs and benefits and we try to figure out the most efficient way to accomplish what we need to accomplish at a politically acceptable cost. Now, 2 decades ago, 2 billion people lived in poverty, according to the World Bank. The 1.9% growth in aggregate income per capita reduced global poverty by about 2/3 across the past 30 years. And in addition, we've seen the average life expectancy increase from 64 to 73 years of age. So there's a really strong incentive to get more bang, dollar value of goods and services produced for the buck, the cost of all these inputs that we put in there. Now, one of the interesting things is when you look at production costs, you would assume, well, it's going to reflect the cost of all those inputs at their prevailing prices, but it's also going to internalize some of those byproducts if mechanisms exist. So if there's a legal system that makes a producer liable for injuring or killing somebody on the job, that's a way that the cost gets internalized to the producer. The court will award the damages, and the producer's going to have to pay more, or the producer's paying insurance to cover themselves. One way or the other, they're internalizing that cost. If a mechanism doesn't exist to internalize that cost, which is typically the case with a CO2 emission, the damage it's doing to the environment is a cost that's uncompensated, and it's held by people around the world now and in the future. It's an uncompensated cost that they have to bear. Now, when we look at what's going on here, we can see that we've got some improvement here in energy efficiency. And so we're able to get more bang for the buck because there's been innovation. One of the biggest reasons why the global GDP grew at the 2.85% and outpaced population and allowed us to grow income per capita is because of technological advances. And what we see here is, to get the most bang for the buck, people have to adopt new technology at a cost-effective pace. And so we've got billions of people around the world making decisions, and we see this improvement in energy efficiency. As a result, the 2.8% growth in GDP around the world meant we only had to increase the energy inputs by 1.7% a year. Okay, so that's the gain we've got from efficiency. Now, when we look at these decentralized decisions that lead to adopting new and improved technologies to create more efficiency, what we see is that the 8 billion people around the world who are all making decisions on how to get the best bang for the buck are coming to the conclusion, they're voting with their actions, that to get the biggest bang for the buck, 80% of the energy input into the global production process is fossil fuels. Now, if you think we're in the midst of a technology-driven energy transition from fossil fuels to non-fossil fuels, let's look at the data. Across the past 30 years, the share of energy into the global production process from non-fossil fuels has gone up 1%. Now you're saying, wait a minute, hasn't wind and solar increased dramatically? Yes. Wind and solar went from nothing across the past 30 years to about 5% of that input. What happened in that non-fossil side is there was an offsetting decline in traditional biomass. This is people that have been using wood and dried manure for cooking and heating. So the non-fossil share hasn't gone up. And when we look into the fossil side, what we see, and Megan referred to this, is coal, the most energy intensive, or the most carbon intensive of the fossil fuels. Coal use has actually gone up 1% in its share of energy inputs. What's interesting is what's gone down is oil's share, and what went up was natural gas share. Oil has a higher carbon content per BTU, so that what we see here is the decline that we've seen, the slight decline in the carbon intensity of fuel inputs globally is less about a move from fossil to non-fossil, and it's more about a substitution within the fossil fuel mix away from oil and towards gas. Now, this tells us another interesting thing, that we've seen the increases in shares on the wind and solar side because we've had technological advance there, but we saw the increase in the gas side because of technological advances. In fact, what's had the biggest impact on the carbon intensity of fuels is the advances in 3D seismic and fracking that made natural gas recoverable at far lower cost. And that's something that is yet to play out around the world. So, when you put this whole thing together, what you see is, we had GDP at 2.8 with efficiency at 1.08. We're able to just have a 1.7% growth rate in fuels, drop carbon intensity by 0.28. It means our CO2 output has been growing across the past 30 years at about 1.5% a year. Now, atmospheric concentrations of CO2 increase 1 part per million for every 7.7 tons of additional CO2 that stay in the atmosphere. So we've seen, in stations that measure this, about a 2.2 part per million per year increase in atmospheric concentration of CO2. Now, if you do your arithmetic, what that says is that over the past 30 years, human beings have been putting an average of about 30 gigatons up. But the increase in CO2 in the atmosphere year over year is about 17 tons. What happened to the rest of it? That's something that we'll look at here because it's got a big impact on thinking through what do we have to do to address climate change. Now, this trend, this upward trend in CO2 is alarming because the increase in atmospheric concentration across this industrial era is altering the carbon cycle that makes the Earth an oasis of life in the black void of space. All right? The U.S. National Oceanographic and Atmospheric Administration notes, the very small amount of carbon dioxide that's in the Earth's atmosphere produces just enough greenhouse effect to raise the Earth's temperature from a -6 degrees Fahrenheit to 59 degrees Fahrenheit. And without the greenhouse effect, water would freeze and the Earth would become just another lifeless planet. So, what we know is energy naturally flows from something that's hotter to something that's cooler. That's why energy goes from the sun to the Earth. But it's also why when the Earth heats up, energy radiates from the Earth into the colder reaches of space. The greenhouse effect occurs because gases, CO2 and the other greenhouse gases, they don't impede the energy coming in from the sun, but they impede the energy leaving the Earth. So that as you increase the amount of CO2 in the atmosphere, we're slowing down the rate at which we're dissipating heat. And the slower we dissipate heat, compared to how we're acquiring heat, the average surface temperature goes up. So that, in a nutshell, is the phenomena. Now, why is CO2 in the atmosphere? It's because we have a carbon cycle. Right? So natural processes, geological and biological and chemical, release about 209 gigatons of carbon into the atmosphere every year. All right? And in the carbon cycle, there are natural sinks that remove carbon from the atmosphere. In the pre-industrial era, human beings put about a ton of CO2 into the atmosphere every year prior to the industrial age. So that's a ton in the atmosphere is 3.67 tons of CO2, just to get the numbers straight here. And so the cumulative amount of anthropogenic emissions in the pre-industrial era across the 300,000 years that modern human beings have been around didn't alter the carbon cycle because the carbon cycle was able to adjust and take the human as well as the natural emissions out. All right? So the human being record across paleoclimatologists build this long-term record of the climate. And when they look at this, what they see is that the climate seems to exhibit a dynamic equilibrium. All right? So that means that we've got a climate system where there are these processes of release of carbon and absorption of carbon, and they tend to be in balance as a steady state. If something perturbs it, creates more CO2 in the atmosphere, we have feedback effects that move us back towards the balance. Now, you've heard a lot about feedback effects that are called positive feedback effects. That doesn't mean they're good. It just means they reinforce the perturbation. So you get more CO2 in the atmosphere, the world gets warmer, ice sheets melt, glaciers retreat, you reflect less of the energy from the sun, which is normally about 7% of it just bounces away because it reflects off of the snow and ice. But with less snow and ice, you're going to create a warmer surface. That's a positive feedback. It's reinforcing the disturbance. A negative feedback, as the name implies, it's not bad, but it's going to do the opposite. You make the world warmer, more CO2 in the atmosphere, it causes a greening effect. So you get more photosynthesis, and the terrestrial and the ocean absorb more CO2 as a result. The world was able to have a cycle that went around about 277 parts per million of CO2 at about that 57 degree Fahrenheit in the pre-industrial era because the negative feedbacks overpowered the positive feedbacks, and we keep moving back towards balance. So one of the key mechanisms in the carbon cycle is this ability of sinks to provide negative feedback effects. So this idea of climate equilibrium is kind of a bedrock of climate scientists. Well, if you have a climate scientist, well, when you're modeling, how much does CO2 affect the temperature? It's a nonlinear relationship. So rather than discuss the different coefficients on a logarithmic function, the way they talk about it is they say, well, what I'm figuring is if we double CO2 concentration in the atmosphere from the pre-industrial level, I'm thinking we're going to have a 3-degree increase. That's what the equilibrium climate sensitivity is all about. It means that when all those feedback effects settle out in the long run, that's where we're going to be. Now, what's interesting then is by understanding this carbon cycle, the dynamic equilibrium, climate scientists can understand the conditions under which we could get to another long-term equilibrium at a higher temperature, average surface temperature. And so the estimates right now are that if we stabilized atmospheric concentrations around 450 parts per million, so pre-industrial is 277, right now we're at about 419. If we stabilize at 450, this equilibrium, all these feedback effects will play out, and we can stabilize at about 2 degrees Celsius above the pre-industrial level. Now, here's that paleoclimatologist data, and there's very fascinating ways. If we had more time, it'd be great to talk about how they come up with this. But if you look at the record here of temperature and CO2 concentrations, you don't see that the perturbations have necessarily been random. There's a pattern here. And back in the 1930s, there was a Serbian mathematician named Milutin Milankovic who identified the cause. He built mathematical models of the way the Earth's orbit goes from a circle to ellipse through time and back again, that the Earth wobbles on its axis and its tilt angle to the sun changes. And he calculated how that affects the solar radiation reaching different latitudes on Earth. And he was able to show the cause and effect, that these astronomical things occur in a predictable pattern, and it explains these perturbations and these long-term climate change that we've seen that puts us into these glacial eras when things are getting colder than average, and interglacial periods when things are getting warmer than average. So he developed these theories, and then in the 1960s, we get computer power that allows the building of the first general circulation models that allow climate scientists to model this carbon cycle and the interaction with temperature and so forth. So in the 70s, climate scientists embedded these Milankovitch equations, ran their models, and predicted the world was going to enter a period of global cooling. So, the February 71 issue of Time magazine, the cover story is The Cooling of America. And then in 75, Newsweek had an article called The Cooling World, and there was all sorts of alarm that this was going to affect agriculture and make life on Earth much more difficult. Now, during the 70s and during the 80s, think back to the criteria we talked about from the National Academy of Sciences, observations didn't line up with the predictions. It said, we're missing something. So Dr. James Hansen at NASA testified in Congress in 1988. He said, look, we've revised the models. They didn't throw out the Milankovitch cause and effect. That's still legitimate. But what was missing was the impact of these increasing anthropogenic CO2 emissions warming the atmosphere. Having included that in the model, running the new simulations, Hansen testified to Congress, it looks like the future involves global warming, not global cooling. Okay, so if we look back then, what's been this negative feedback effect from this increasing 2.2 parts per million per year in atmospheric CO2? What we've seen is the predictable response in the climate system that the ability of the land and the ocean to absorb CO2 from the atmosphere has gone up and up from its pre-industrial level. So when we said, well, where's the rest of that CO2? We're putting 30 up and only 17 seems to be staying up there. The rest of that is, so about half today of the CO2 that people put in the atmosphere doesn't stay there because we've got about 24 gigatons of additional removal from the natural sinks of the land and the ocean. All right. So when we put this all together, what we see is what's happened to cause temperature to go up? It's happened because people have been increasing their CO2 emissions faster than the sinks have been able to increase. And that difference explains exactly what we've seen in the additional CO2 concentrations in the atmosphere. Okay. So, when we think about looking ahead, it looks like the size of this future negative feedback effect, these sinks, is pretty important. Now, I mentioned the IPCC does those annual or those assessment reports. In the third assessment report, they looked at the carbon cycle and they predicted that as CO2 emissions concentrations in the atmosphere go up, sinks are going to continue to go up, but at a slower rate. And so, all right. And so, if this is the background Last year you had Paul Romer, who I didn't know till I came today, is on the faculty here, which is great news. He got the Nobel in 2018. He was a co-recipient. The other person that got him was William Nordhaus from Yale. Nordhaus, from back in the 70s, tried to link up all of this climate knowledge and modeling with economic models. Because he said, look, if we're going to address climate change, we've got to find the point at which those benefits of using energy, particularly the fossil fuels, are going to be equal, the marginal benefits are equal to the marginal costs. And so he did estimations of what that crossover point looks like. And Megan had made the comment that to economists, the best, simplest, and most efficient solution is just put a price on carbon. That was the focus of Nordhaus. And so his early work was to estimate what would be the appropriate charge to put on carbon. That way people would be internalizing those damages, and then everybody, all those decentralized decisions that people make around the world would take into account the costs and benefits of using fossil fuels, and we would then start to use the right amount. Now, what's interesting about this is when you look at Nordhaus's work, he estimates what that cost should be, and people often refer to this as the social cost of carbon. That's the dollar amount that's appropriate to put on carbon worldwide to solve this problem. And I think the important piece here is that Nordhaus's work, where he says, let's balance the costs and benefits, it says that eventually we need to reduce emissions, but not eliminate them. So this analysis is saying we don't need to get to net zero. We need to get to a point where the benefits and the costs of CO2 emissions are brought into balance. Now, I was able to do some work in that senior fellowship that Dan mentioned in the introduction. And what I did was I took the electric system in the US, and I said, what if we put different charges on CO2, allowed the power system to make cost-effective technology turnover, where would we be at different price levels? And you can see that the higher you make your cost of carbon, the more it's going to make it cost-effective to shift to less carbon-intensive output. And the result here, though, is very different from what you saw with Jacobson. That we're looking at, if we put a $50 per ton charge on, which is what people typically talk about with this social cost of carbon, we're going to have about a 25% increase in the price of electricity. Now, that's going to do a lot of good things for us. It's going to create greater efficiency incentives. People are going to reduce their demand. It's also going to create this shift in the carbon intensity of electric production. And if we took the revenues from that charge and used it to try to address some of these regressive cost impacts, you know, the net effect, if we recycle those revenues, can be that 13% or so, to get a 50% reduction from the 2018 levels. So you can see the challenge here. The challenge here is we've got to do the most cost-effective things to reduce CO2 and get the job done, and it's got to be done at a politically acceptable cost, and that's not easy. This is not going to be inexpensive to do. All right? So it's really important that people that are building climate policy understand these kinds of cost-benefit trade-offs. And remember, that was the mission of the IPCC, to give people the information they need, reliable predictions about how far and how fast we need to reduce CO2 emissions. So, one of the things about the reduction in CO2 is this has to be a global effort. Why? Because the atmosphere effectively mixes greenhouse gases. So you emit CO2 anywhere, it has the same warming impact everywhere. So no one person or nation can solve the global warming problem on their own or for themselves. So you need a concerted effort. Now, what's interesting is when William Nordhaus first set up his model to look at those costs and benefits, he had good estimates of the cost of moving away from carbon-based fuels. But he didn't have good estimates of the benefits to find that crossover point. So his initial run, he said, I'm going to make a constraint that we don't go above 2 degrees Celsius from the pre-industrial level. Where did he get that? He looked at one of those paleoclimatologist graphs, and he said, here's where we are. If we go 2 degrees more, we're going to get outside of that range that we had bouncing around that equilibrium. But he said, look, as a first cut, I'm going to use the 2-degree constraint. But it's unsatisfactory from an analytical standpoint. But I'm using it just to take a first cut. Let's get a ballpark estimate of what that social cost of carbon looks like. But that anchored the discussion about what the world ought to do. In fact, when Nordhaus received his Nobel Prize in 2018, he has a speech, and he made a point in his speech to say that he still has major reservations about this 2-degree target. But nevertheless, the Paris Climate Agreement embeds this 1.5 to 2-degree limit as the collective goal for the world on climate change. Now, that's something that most people know about the Paris Climate Agreement language. Most people haven't paid much attention to the other piece, which is how are we going to accomplish this? And the Paris Climate Agreement does not say we've got to get to net zero. The idea of net zero was around. There were people pushing the language to incorporate net zero, but it doesn't. It says we need to restore a balance between what people are putting into the atmosphere and what's getting taken out of the atmosphere every year. All right? So, we had the AR5 report that came out to give people an indication how far and how fast do we need to reduce CO2 emissions to get to these temperature targets that we set in Paris. And so what the AR5 report said was that if you look at emissions from 2011 on, the world cannot emit more than 400 gigatons cumulatively before we're going to hit 1.5 degrees. And so the world hit 400 gigatons of cumulative emissions from 2011 last year. But as Megan pointed out, we're only at 1.1 degrees Celsius, not 1.5. The warming impact that we saw in the AR5 was, it grossly overestimated the warming impact that we actually observed by about a factor of 3. Logically, you should ask the question, what was the AR5 missing? And if you look at the assumptions that went into the AR5, the assumptions were that the increase in natural sinks, instead of increasing more as concentrations go up, the way the IPCC AR3 says the best available science indicates, they assumed it would decline to virtually nothing by about 2080. So that negative feedback effect would break down. Now, if you have an assumption that underestimates the sinks taking out of the atmosphere, and you run that simulation out through time, and the sinks don't decline, you are going to overestimate warming impact. In fact, the only way you can have a finite limit on the amount of CO2 that people can put out is if you don't have any offsetting take by the sinks. That's the only way you can have a finite limit. If the sinks are above the pre-industrial level, there is a sustainable level of human CO2 emissions that won't increase concentrations and won't increase global warming. The update that was presented from the AR5 came out in this AR6 summary report that I just talked about that came out in March. And the update is that we face a finite limit going forward to achieve the 1.5 degree goal. We can emit another 500 gigatons. So instead of the headline on the summary report saying, hey, the good news here is we grossly overestimated the warming impact of CO2. We've got a lot more time than we thought to try to deal with this problem. You don't hear that. But we've had this dramatic revision, and it doesn't look like what was missing in the analysis has been fixed. Now, so here's that AR6 report with the new estimate. And what was really interesting to me was there's a new little buried caveat in the AR6 summary report that's down here on the bottom. And it says, look, these are modeled scenarios. We're exploring future emission levels, climate change, related impacts. There's a range of assumptions that we use here. These are quantitative projections and are neither predictions nor forecasts. Now, when you think of what do people who are trying to put together climate policy need, they need a reliable prediction of how far and how fast we need to reduce CO2 emissions to meet our collective temperature goal. If you had tried to do your part to meet the initial indication you got from AR5 and get to net zero by last year, you would have incurred far more costs than are necessary to reduce your CO2 emissions. You would have created a competitive disadvantage for yourself in the global marketplace and created a regressive cost impact as a result. Again, other than that, it looks like it would work. All right, so what's interesting is ahead of COP21, there was another group called the Under 2 Coalition that formed up. And it formed up around this idea that if you want to hit these long-term targets, we need to get to about 2 metric tons of CO2 emissions per person before we get to 1.5 degrees. Now, the logic for this is pretty straightforward. If we get into a world of 450 parts per million, we're going to move from where we were when this came out so that the sinks are going to be at least 20 gigatons big. Right now, as I look at it, I'll bet at 450 we're going to be closer to 30 gigatons. But at the time, they said it's a good bet we'll get to at least 20. And the projection is that global population, the expected trend is we're going to grow and then flatten out at about 10 billion people in 2050 and beyond. So if you can have a sustainable amount of emissions of about 20 gigatons a year with 10 billion people, bingo, 2 tons per person ought to do the job. And if, as it looks right now, we'll be closer to 30 in that than 3 tons per person. Now, where are we right now? If you look at the axis here, pounds of CO2 per dollar of GDP is on the y-axis. The x-axis here is dollars of GDP per capita. If you multiply those two things together, you're going to get CO2 per person. So all of the x and y points that you multiply together and can get 2 tons per person are that lower curve. All of the points you can multiply together to get 3 tons are the higher curve there. And at the very top there, you see the year-by-year observations on those two parameters and the pathway that the world seems to be taking, which is we seem to be wandering along a 4-ton per person level. So when we think about the challenges ahead, it's going to be far less expensive to go from where we are right now to 3 tons per person. It's going to be more expensive to go to 2. It's going to be inordinately expensive to try to get to net zero. Now, these kinds of targets are really important. Think of India, for example, and the US. If you think we need to get to net zero, since 2007, in the US, we've reduced our CO2 emissions by 20%. We're going in the direction to get to net zero. If you're India, in the same time frame, your CO2 emissions have gone up 88%. You're not doing what you should be doing from that perspective. But let's think about it. If we need to get to 2 or 3 tons per person, India right now is at 2 tons per person. If the whole world had the carbon footprint of the typical Indian citizen, we would have solved our global warming problem. So from their perspective, it's not, they can keep increasing CO2 at the rate of their population increase and stay at 2, and it may be that they've got room even to move to 3. But they're being criticized by the US for their emission trends, where people have a carbon footprint of 14 tons per person. All right, so what do we expect going forward? We expect this net zero target is going to create a wedge internationally between countries like India and countries like Europe and the US. I also think that when AR7 comes out in another 7 years or so, I think they're going to give up on the idea that we're going to be able to get to net zero by 2050. And we're actually seeing a little bit of a signal in that way that although the reports the IPCC puts out say net zero is you got to take out what you put up, there's a UN coalition of countries that have committed to net zero, and they're defining net zero in their publications a little bit different. They're saying you need to reduce your CO2 emissions down to levels where the forests and the oceans can take away the rest of it. So there's, I think, a little bit of indication here that we may be moving towards redefining the net zero target that takes into account what's being taken out by the sinks. I think we'll also see, as the years go by, that the world community is going to give up on 1.5 degrees because it's just going to look like it's impossible. And they're going to focus then on 2 as the target. And we're already seeing some of that in that AR6 report that came out. They said, you know, on a cost-benefit basis, it's pretty clear that doing 2 degrees makes sense. We can't say that for 1.5. So I think you're already seeing a little bit of signal that that may be the direction that we're going. So when you look at the challenges that lay ahead to address climate change, it looks like we need good information that looks at the costs and benefits of solving this problem, and we use that to construct politically feasible and politically tolerable climate policies going forward.
Thank you, Larry. I think we have time for a couple of questions before we go to lunch. I see one right down here in front.
Thanks for the presentation. Good information there. If I could maybe take the pro-net zero standpoint, a couple of elements of it. Oh, thank you. If I could take the pro-net zero standpoint, first, you know, we can't run the risk that climate sinks might not increase. You know, we have to guard against that. And secondly, that we can innovate our way to paradise. You know, costs of and productivity of wind and solar have improved, you know, probably quickly than most people expected. We have maybe hydrogen and even fusion on the horizon, so that if we continue to invest, we're just going to reduce the costs of going to net zero dramatically. So how do you incorporate that into your analysis, and maybe also think about the opportunity cost of investing in net zero versus other areas?
Okay, good. Another appealing idea that a lot of people want to believe is true is that we can invent the world that we want, and that technological innovation is going to ride to the rescue and make this transition to net zero low cost, or at least a politically tolerable cost. And when people talk about that, more often than not, they'll say, hey, I'm optimistic about the ability of people to innovate and create the technology we need. Now, in 2002, Daniel Kahneman won the Nobel Prize in economics, and he was a psychologist. And he won it because of his work in behavioral economics. And he's got a book out, it's called Fast and Slow Thinking. And what he says there is that there are predictable errors we make in the way we accumulate, process, and come to conclusions about information. And one of the most obvious biases of our human nature is a bias towards optimism. And behavioral economists like Kahneman define optimism as viewing oneself, the world, in the future in a far more favorable light than is objectively justified. So, I would love to be optimistic about our ability to invent the future, which is why I was pointing out that we've got as much of an incentive around the world to improve the technology on fossil fuel use as we do on renewables. And an example for that is, what is the biggest competitive obstacle for electric vehicles? It's the Prius. It's a hybrid. You know, in Europe, they had to outlaw diesel hybrid cars because they were so good. It meant that we'll never get the electric penetration that we want in electric vehicles. So I think as much as we'd like to think technology is going to ride to the rescue, it doesn't always. So people will give you examples of cell phones and so forth, but they don't focus on examples like nuclear power that came about, and people thought as we went up the learning curve, as costs would decline, electricity would become too cheap to meter. That's a technological optimism that never played out. So I think we have to be very careful with that. And then the other question was on net zero. Oh, you don't want to take the risk. Which is why then, why don't we develop a policy because that depends on and changes depending upon what we're observing on sinks and emissions per capita. One of the real advantages here is some of the most accurate and up-to-date information we have is on how much we're putting up there every year and how much is getting taken out. So we can develop a policy that hinges and changes if we observe a change from what we expect on the sinks.
We have time for one last question. Yeah, gentleman here.
I would just ask the question of things, the unintended consequences. So, hydrologic cycle, the rainforest, you know what you have in the ground for trees in Brazil, Amazon. Then the water temperature in the ocean's rising, and the way the water moves up and down has a cooling effect. And these are massive interactive systems, and they're all moving in the wrong direction. So I'm just wondering, whatever the homeostasis that you had for your sink, up and down, whatever the actors are in that are less consequent, are deteriorating. Coral reef, temperature, water, trees, all the things that are working against us. Can we actually, and then I'll just say this, you have the European weather system modeling in the US. We don't even agree on how to model the weather.
Right.
So just put that into the equation, and I'm just being the devil's advocate that we probably should do more sooner, better, with less carbon.
Yep. So there's a couple of things that you raised with that question. One is, and when I've talked about this before with people, I often get this question, well, wait a minute, you're talking about if we achieve 2 degrees, 1.5 to 2 degrees, and we're at 1.1 right now, we're going to have global warming that is 50 to 100% higher than it is right now. And people say, now wait, why would you want to do that? Because the oceans are going to be getting more acidic, more acid. We're going to have more environmental damage. Here's the problem. You can't do any better than the collective agreement. If you do anything more than your share to reach the 1.5 to 2 degree goal, all that means is other people have to do less. Because all they've committed to is that they're going to contribute to getting to 1.5 to 2. So even if everybody did contribute to that, and you don't like it, you'd like to do better, you don't have a choice. You can't do better than the collective target. And the real problem with this, and I think Megan touched on it too, is it requires cooperation. If you look at game theory, the way this is set up, we're all better off if everybody does their part to reach the climate temperature goal. You as an individual are even better off if you make a commitment, don't incur the costs, and have everybody else make their commitments, because your impact is negligible. So that we've got a system based on making voluntary commitments to do your part, where game theory tells us the dominant strategy is to say one thing and do another. And that's partly responsible why, despite 30 years of international efforts to bend that curve, we're not seeing any reduction right now in the pace of CO2 emissions year over year.
All right.
Okay, thank you.
Larry, thank you.